All right. So thank you very much, everybody, for joining. This morning, I would like to discuss some of my thoughts on express intent. I'm sure you are aware of the CPP core guidelines and how they help us write good implementations. What I strive to do, and what these guidelines also help us to do, is to have implementations which are easy to use correctly and difficult to use incorrectly. And today, in the light of some of the new C++23 features and some features which we have in C++ from before that, either C++ 2017, we are going to look at some of these features and how they help us in this objective of ours. As it was mentioned in the introduction, this is my second talk. Oh, I forgot to include two of N. So this is my second talk on this topic. Previously, I had talked on this. That was a while ago, I guess, and we touched upon some of the things that the CPP core guidelines actually recommend on this item. So what do we want? We want some indispensable qualities in our implementations. We want clean and direct implementations where the clarity of intent is there and it is evident the moment you see the code. Its use should be evident the moment you see how it is implemented, or you see an API, even if you don't see the implementation inside. And it should result in correct use. You should not fall in traps. Okay, there should not be strings attached or fine prints. Ideally, that's what we want. And we want safety, and the language and the library needs to enable these kind of things for us. And that's the discussion topic today. Why are they indispensable? Because maintainability is key to the survival of our products and long-term life of our implementations. The speed at which you can go in implementation, not just initially in a green field, but in a brown field in an existing product, debuggability, response time. There are many such qualities that you would like to have in your products, which is what the express intent also helps us go towards. If you are a company, we always see this kind of a thing, like you are a startup or a small company which started just somehow bringing things together, then they didn't have time to do it well. More often than not, and I would like to say mostly, they have to come back and revisit. So these are the things which hit you sometime in the long run, and you're always trading something for something else. Who am I? I'm an architect working with Expo, and in this forum, I have to say, I can tell this to anybody that I learn languages, but in this forum, I have to mention specifically that I like learning natural languages. You might see me talking in more than one languages, thanks to uh, our setup and our diversity, as well as the interest that I have. And my mother tongue remains to be C++. High performance products is what I love to work on. I have worked on a series of such endeavors of making products high performance, etc. Cloud native is the theme that I'm working on these days. Getting ready for distributed systems and still achieve the high performance which you would assume in a uh, in a in a uh, in a machine that you totally control on a local setup, or a physical machine. But with cloud native, you have to ensure these kind of things, and that makes it pretty interesting. At CPP India, I'm usually around, so just nudge me or contact me on any of these. More than happy to discuss any of these, or any quality or transformations or issues or improvements that you want to discuss at your end. Enough about me, and about the code. So, in your code, does your head start to spin the moment you try to look inside and you're not able to figure out and understand what's really happening? As soon as you try to take a look at the code and the way it is implemented, do you feel the need that an expert is a must in order to guide you? Unless told, you might not be able to figure out what's really happening. And I've seen a, I didn't include it here. I've seen a very funny cartoon strip where it says, this function is called as get employee. What do you think it does? I don't know. It could do anything, was the reply by another one. So that was a fun take on the things. But the dependency on a person or on the original author in order to guide you through code, guide somebody else who's not the original author, or yourself in a few months, is not sustainable. And if you need usage instructions or assembly instructions, you are somewhere missing the point. So today's discussion, I would like to take up on these kind of things, where even a newbie should be able to find a way. We will try to take some opportunities to learn some of the new things which on the way that we come across. But a newbie should be able to help themselves. They are programmers, but they don't know your code base, and it should be very easy for them to get on. Okay. And the way the code should be there is how you, if you have assembled any furniture, it can be assembled in just the one right way and not any other way. So we have to make our implementations also just like that. You can't flip it and try to attach it. It's just not possible. So we need to strive for these kind of things in our implementations. Very much a very good quality to have. What it means is where in a not well uh, written implementation, where everything just goes downhill and you sort of feel the lack of control as to what's happening. You don't know why something else is messed up because you made a change in one subsystem or something. uh, it feels like a fall. Rather than that, we would like to fall in the pit of success. In this valley, there is resistance to go uh, away from the good spot that you're in. Okay. And that's something in the light of uh, the recommendations in the CPP core guidelines, I would like to have this discussion today. So if we see, I've just opened the page on the ISO CPP website. You will see that there are core guidelines on the top. If you see, the core guidelines are split into sections, and one of the sections is philosophy. Okay. And you would think, why philosophy? If you see philosophy talks about many good things which are which you cannot encode clearly in language all the time, but they are the intents that we want to have in the code. And there, that's why the section is called as starts with P, and P.3 is the express intent item that we talk about. This page gives you all the rules or guidelines. I'm sorry, they are not rules. They are guidelines to have good and healthy implementations at your end. And this one specifically really interests me. These basic kind of things was something that we have discussed in the first version of my talk. This second one, I would like to go further into other interpretations because it's philosophy. And you can extend it and extrapolate and interpolate into other things. So that's what we want to do. It's just not possible to do it the wrong way around. Let's consider this. Okay. Here we have two vectors coming. One is a vector of files in the first line. I'll just go for the laser pointer. Okay. The first one is a list of files which you get from somewhere, and a list of metadata that you get from somewhere else. And the idea is that the metadata belongs to the files, but the sources are different. And you get these things and you send this across. Okay. So obviously you have this send which takes the files and the metadata and it tries to send somewhere. Okay. Uh, a slight mention here. This code is C++23 because of the integer literal that I've used here. If you see here, this uz is a new introduction in C++23 for specifying that the data type here, this zero, is an unsigned size t. So if you see, this is an excerpt from the integer literal page of cppreference.com .org, or is it .com? I think it's cppreference.com. And you see it mentions that now we have the suffix. You might have known that we have the suffix of u, we have the suffix of f for floats, u for unsigned, but now we can add z also to it to say that we are compliant with size t. When I had written this code on before placing it on the slide, I had used just an int, just a zero, and it complained to me with high level of warnings that I was comparing signed and unsigned. So it's very helpful that you are able to specify this with the suffix. And as you see here, this is the example from the same CPP reference web page. If you specify 0 uz, its data type is the same as size t. And if you specify just z, you can even have the integral, sorry, the signed equivalent of the same size t. So it would have the same number of bits in the memory, and it is just going to be signed. So very handy. I just would like to encourage you to first switch to C++23, and of course, be benefited by this. So looking at this, do you see everything is all right? Uh, During this talk, if you have any questions, please feel free to unmute, interrupt me, and we should talk on the slide rather than later. So, what do you think? Everything good here? Obviously, when I'm asking, can somebody tell me what might not be right here?
So the size of metadata, like I think it's like the number of files that you have,
Yes,
number of
perfect.
elements.
Thank you very much. So number of items in files and metadata may not be same. Would this code pass your code review? Would this be accepted? Would this work? Because you're depending on the file size. Uh, and assuming that the size of metadata is the same. It might be the case, but is it assured? Is it guaranteed? And it's not clear that that is the case. And that's the image that I got from Microsoft when working on the PowerPoint for a bomb. So that's a bomb, guys. uh, very sweaty because of the error. So yes, that is the issue. And obviously, we don't want this kind of a loophole in the system. It would be rejected in your code reviews for sure. Okay, and why? Because really, what we want is to express the intent. Here, we don't want the files to move independently of the metadata or both of them to be out of step. Really, we need to be in lockstep and both to move together. And so, very much, they are pretty much tied to each other. So, what's the idea? Let's pair them up. So, let's see what we can do here. Uh, we can ask for the pairs to be made out of the files and metadata. Okay, so obviously we need something called as make pairs. You might remember that in the standard library there is make pair, but that is just for two items and it makes one pair. Here we want to make pairs of entire vectors or any containers here. So we have to implement the span version of it. The span version of it would have been best, but I'm using vector here. But if you use a span from C++20 instead of the two vectors, if you have two spans, it would be much better, and it can accept and work on more than vectors. It could work on arrays, C style or std array, or other contiguous data structures. And then you are able to send. That's the send call, which is finally made based on the pairs that this make pairs created. Okay, if we just look a peep inside, that's what the make pairs would have, the two vectors, and here we would tie them together. So this code is transforming the files and metadata and inserting as pairs into into the vector, into the resultant vector. Okay, and the real magic is done there, which is the make pair std that I just alluded about previously. I'm sure you're all aware of that. So you take a and b, you get a pair of a and b, and for all a's in the first vector and for all b's in the second vector, you have now made a pair. Okay, is this going to work? And then of course you do the send, and now the send is going to take a pair of vectors. And this is where this higher level abstraction of a pair is eliminating the need for having out of step data at all. And as you see, you are able to pick the two items first and second and send across, uh, really do whatever you wanted to do with them. So, so this is how the abstraction here of 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 demanding a pair and not just two and not two vectors is allowing the user and forcing the user to actually make the pairs and then send them, so that you are sure that this code will always succeed. You can't have one of the items in a pair, and if you have an entry in the vector, you would have both. Okay, good. So this kind of a higher level abstraction would help you, and the interface is forcing you to uh, make the pairs at your end and then pass to this for correctness. And there is no way that you could use this incorrectly. Okay. And if you switch to C++17, you could deconstruct the pair, not have to write the first and the second, because they are not the domain the domain items of this code. The domain items of this code are the file and the metadata. And this structured binding introduced in C++17 would deconstruct the pair, and you can actually give names to the two items rather than stay with first and second. Or if you have a tuple, you don't have to write get 0, get 1, get 2 for getting the elements from the tuple. And so you have essentially zipped the two things up into pairs, and every link there is having an item from the left as well as the right. Okay, all good so far?
I have one question, Ankur, on the
Go ahead.
implementation of make pairs.
We can go back here.
Yeah,
Make pairs.
make pairs.
Yes, there we are.
Yeah. So now it's expected that, right, that where whatever we are passing to this make pairs is like, both have the same length, correct?
Exactly. You got
So
that right.
instead of solving a problem, what we did, we just took a problem from one point, and if the problem is still there, but we just shift it to some another place. So it's not solving a problem actually, right?
Very good point. Yes, that was the whole point. Uh, we just changed the loop, or a possible loop into a transform, but really we have not had any change. So if I just go a little back to the uh, starting implementation, this one, okay, this one was handling both the vectors and assuming that they were the same. But now, with the change, the send function is always correct. You cannot have inconsistent data inside the send and have any surprises. Either you access data which is not there, or you have partial work done and there is consistency. There wasn't a clarity in the behavior. What will happen if both the vectors are having different sizes? Yes, we have just moved the problem from inside send to inside make pairs, but we have moved the problem to the domain in which where it belonged. Inside the send function, you don't want to have or enforce requirements, because the job of that function is to send. You cannot have assumptions put in, and you should not have more work done than what that function needs to do. And rightly so, somebody has this problem and somebody will have to work on it. The user is now forced to write this make pairs and make the pairs at their end, which is their domain. They know where the files came from, they know where the metadata came from, and they know how they can be consistent. And it's up to them Yes, it is a transfer, but it is transferred to the right owner of the problem and not the send function. Make sense?
Yeah.
Okay. And I see we have a problem. Inherent problem is the files and metadata are not together. But we face a lot of these real life situations where the items and another set of items are really together, but they truly come from different places. For example, you have a set of keys and a number of updates or mutations to add into a database, and you have the database rows. They are really two different places. You have to get them both in one place, make sure the update happens, and then you save the database, save the changes back, or you do a third thing with it. It's a very normal kind of a situation which you might land into. Okay, we should truly avoid to not have that. And truly here I'm using pair here, but I would say even a named object of your data type, which makes sense to the domain of the implementation, is ideally the right thing to do. So you don't want a pair of path and string. It still doesn't tell you what is this path and what is this string. But if you have let's say a f- a file to be sent, or let's call it send info. Bad name. If you have info in your name, you've not got it. But let's say file detail. So if you have a file detail, and that is the pair, even if it is just a pair bringing two things together, that small struct really speaks because you named it so. And that's what I would recommend here. Okay. I'm sticking with pair here, but that's a much better one. Instead of using a tuple or a pair, if you can actually name your data type, it would be much better and make sense to the business domain. And you don't get bogged down with the technical details and the implementation details. Rather than that, you stay on your business domain and really solve the business problem at hand. I'll go ahead. So zipping, like I was saying, zipping things together is pretty common. We have also in C++23. I had included something about the flat map, but we have had flat map in Boost. You all know about map. Map is a node-based associative container where you have a key and a value associated together. Of course, we all know that, but it is node-based is the key. Node-based forces that the map has to allocate every node from the free store. It might have the allocator, you might have some optimizations, but you still are randomly placed in memory, and you have to ask for a node to be allocated and the tree to be formed of nodes, and every rotation or balancing of the tree would result internally in the map all of these things to be shuffled, and it would cause your random access in memory, slow you down, etc. So in order to address that, the flat map, we should cover this in some other talk, but a flat map is a very handy data structure where you have, let's say the map actually doesn't have a node with the key and value, but it has the keys in a vector and the values in a vector. Because guess what? When you're trying to look up, find, match, insert, more often than not, you touch the key, you match the key, uh, you're playing with the key more, and finally you play with one value which you came to set in the map. Map by definition is having unique elements for every key. So you want to do the keys, but every node that you load in your cache, you have the key as well as the value, and that pushes the other keys into the next cache line, and you have to load that one also, and it hits performance. So that's that about flat map. I would like you to go back and explore, and maybe we could talk someday about flat map and flat set. There is in the CPP reference, there is mention about flat multi-map and flat multi-set also. I don't know if that is a C++23 thing or a C++26 thing. Sorry about that, I don't remember. So this is a good one, but here you have two vectors, a key and a value vector, and you would like to tie them sometime together in if you want to have an iteration view of the pairs. And this zipping is such a common is such a necessary thing inside them. Zip the two vectors. You could have, this is the example that I just discussed. You have a set of uh, mutations or updates to make in the database against the fetched rows from the database, which you change and put back. That's two data sets coming from different places. You have a list of students and a list of results. They're coming from different places. Now you want to send them across because maybe the results are coming from a place where the student is not connected to it. You don't want the student data to be visible, etc. So it is just results against an ID. And here, this all the students are there against the ID. So uh, you want to zip them together. If you think about it, even in your unit tests, you might have expected and actuals for a set of things, for many things, not just one item, but maybe you got something from a set and you have an expected response, many items, and an actual response, many items, and you want to match them together. You might want to zip them and look for equality. There are algorithms, of course, which help you also here, but this is also an example of where data comes from two different places. So, latest fashion in C++, zip it up. And if we use ranges with the previous one, you can see that this is the function that we had from before. This is the first version where it was working on two different vectors. And here the assumption was that the sizes are the same. If we don't want to iterate, sorry, if we want to use the C++23 facilities, we might want to transform this something like this. As you see here, this loop has now changed into a zip, and the version of the language is now C++23 because zip is available in C++23. It does exactly what we have been talking about. Take the two elements together and treat them, work on them together. Okay, so this actually simplifies the internal implementation around zipping. And this is what the user would write in their make pairs, how the user is also helped. Now we don't need this make pairs at all, in fact, because it can be just shelled. I love deleting code because you can write it in a better way or with less code, and you could just do a zip. So inside the make pairs, or now you don't even need the make pairs. You could just zip the things together to uh, make the pair of the vector of pairs that you really wanted. And what happens if the ranges have different sizes? So I don't have the C++23 tag here. I'll add it before I publish the slides. But this is C++23. Let's say we have these three data sets, and they are all different types: a vector, a list, and an array. And they are all different sizes. The first one is 4, has size 4. This one has size 5, and this one has size 6. And you see that's what you get if you print them. Okay, I'm not showing every piece of the code, but just the relevant ones, this slide where. So here now we want to print the zipped version of these, and please note now we have three of them. So zip is going to work with any number of uh, ranges, which themselves bring in elements, and all of the ranges are working together. As you see here, we have a tuple of references to the original elements. So we have the reference of int, string, and char here in this tuple element, which is provided by the zip view of C++23. Okay. And if you had to just print them, all we are doing is, now that they are tied together, you could do something good with them, some business logic. If we just print them, that's how you would do it. Because it's a tuple, you will get the 0th item, first item, and the second item, and that's how you get the output here. Okay, so as you see here, size 4, size 5, and size 6 have been iterated by zip, and zip guarantees that the iteration would go only as far as all elements are present. So if they are of different sizes, you might not proceed on to the items which are not uh, not there in the other data in the other spans or in the other data structures, other containers. And so, as you see, if we just edit them, now that our tuple is a tuple of references, we get the character and make it lowercase, maybe, or make it, yeah, make it lowercase. And when we print it, we see that the original vector z is now having a, b, c, d of lowercase, but ef stay at as uppercase because this loop iterated only 4 times because of the first vector, which had only 4 elements. The fifth element of the second vector and the fifth and the sixth element of the third vector were not touched, they were not iterated, as this thing proves. This example is from the CPP reference, but this tells you that there is safety also when you work with them. It's so different. If you remember the original implementation that we had where we were accessing the ith position in both vectors, from there, if we come here, we have a guarantee, and we are not having to do the low level checks, or maybe there is optimization here, uh, which helps us not to spend as much time as checking that you are exceeding in every loop. Or maybe you could get smart. You would have to write code by hand by checking what is the least size of the two vectors that you are working with, and maybe just iterate that many number of times. But you don't have to remember or do any of that. So that's what the zip view from C++ 23 gives you. Um, I think I had this link, and as we see here, it works on variadic templates, so you can give any number of items to the zip here. Any question here? So the user is now helped. They don't have to write the code. All right, I'll move on. It gets sweeter. You can have a zip transform view, and this is a similar kind of an example uh, where you have a vector of 3 items, another list of 4 items, and an array of 5 items here. And you have something that can add 3 things together. And if you use the zip transform here, you could give the callable here, which would take the 3 elements, and you are not bound to make a tuple out of them. They stay as 3 elements because once you have a tuple, it then becomes one thing, and then you have to access the internals, the 3 items inside there with a get, or if it's a pair, you would have to use first and second. Here, they stay as 3 different elements, and they are directly passed as 3 elements into the callable that is passed as the first item here. And this zip transform would transform the 3 things and give you a result. What is the data type of result? Any guesses? I know you might not have seen, but somebody wants to try.
Tuple.
Span of pair.
Good.
Oh, sorry.
Sorry.
It's a zip transform. Okay, okay. No.
So, tuple is a very good answer, but tuple is just one element. And here we are working on many elements inside this vector. This would actually iterate them and give you n elements back. And so it happens to be. I think I might have deleted this, but it is itself a container, and it might be. I think I have the link or. No, I think I'll have to go back here, and because I'm using Blazor. Okay, maybe I didn't put the link. but I might have the web page open here. Zip transform view. So here, this sum happens to be, yeah, so we don't see what it is. The sum happens to be an output range, I guess, and it is instantiated here itself on this line. So maybe we want to see what that does. Um,
So it says that it produces zip, sorry, it produces view as a result.
oh, it produces a view as a result, right?
Yeah.
So I would, yeah, that's what I was trying to do. What was it? Type ID, type, not type traits.
Type info. Type
Type
info.
info.
Type
Thank you very much.
type underscore info, I think.
No, I guess. You see that that's a problem. Type underscore traits is the right header, and type info without the underscore is the right header. As we see here, the error was not given. So here we have the zip transform is not a member of views. Hello, what's the problem? This is a working example, and how can it not run? So,
So GC 12.1.
this one is better than that. 12.1. Oh, yeah, but that's the one this guy has. Even if I like, I've not done any change. Let me just remove this. And so surprising because the code examples of CPP reference usually work. Views, zip transform.
Not all of them work.
Yeah, I guess. Come on, this compilation itself is not using the right. I think if I copy and paste this into another website for Compiler Explorer, maybe it'll work. But we'll leave that for another day. So so actually, C++ for 23 has come up with, I guess this is you don't have to instantiate the sum beforehand, and that's an addition in C++ 23. It remains to be studied by me, but I think I saw enough to be able to comment this that you can have infinite ranges and you can have output ranges coming out of this, and they have been introduced in 23. Okay,
So
and so the output here is this. Sum is itself a vector, and uh, and or it's a view. It is I don't know physically what it is, but this guy is adding the items in the v1, v2, v3, and you see the sum for every corresponding element is printed here. As we expect, the zip will go on only up to the least sized range, and there we have this.
So Ankur, I have a question. So is this zip transform is again like a lazy evaluation, or it will happen as soon as you call add to sum is equal to std view transform?
Now this one is not lazy.
This one is not lazy. I mean that
This one
means
is
then
not
we
lazy.
have,
The
then we
view
have
is
to
just creating a view, but this one is not lazy.
okay. So because
Uh,
if it's not lazy, then we can't have an infinite range kind of thing, right? There.
you might um because that's a specification of, let's say, v1 is infinite. Oh, if it needs to have the size upfront, then it might not be lazy. But you could make it lazy. No, not lazy, but at least be able to handle. infinite ranges. Sorry, I didn't mean lazy. Yeah, this is definitely not going to be lazy, and this is just doing the execution right there.
Okay.
But if v1 is infinite, it might never end for v1 because of v1. But if the other two are finite, then it'll end because of them. But if all the ranges are infinite, it could go infinitely and it'll stay inside zip transform maybe here. So maybe you say process events here or events from 1 2 3 or something, and you could just have your I'm thinking aloud here. You can have your, what do you call, the event loop inside there. A weird way of having it, but
But views in
it's
general
still a
are lazy,
question.
right?
Sorry.
The views in general are evaluated lazily, right? So,
Yes,
I mean,
exactly.
it could also be possible that the same stuff what you see in the output could be evaluated lazily. Just because we are accessing V1 here completely and doing the print, maybe at that point in time it gets evaluated. I mean, a simple test would have been maybe just to access one particular element in that range rather than the entire range. Yeah, but something I think we can
Yeah,
write
but
in
but but
compiler
the
as
way
well.
you the way you do it with views, etc. Let's go to zip view. So if you see the example here, here the zip view example has this what we discussed on the slide. Here you have created a view, but you need the loop to go through them. Okay, so this one really needs you to have a loop. So once you define the zip transform view, you might want to do it. But if you just want to create the uh, you know the mechanism and iterate it yourself doing other things, then I guess you would use views, the zip view. But if you want a transformation to happen like the transform that we were using in our code also on the previous slides for making the ranges, you need it there and you need nothing else, so you could just go ahead with the zip transform. But yes, ranges are usually lazy. This one doesn't look like. Okay, but thank you for the good question. I guess made me think in a new direction also. All right, so let's zip that topic up. And and then this is something that uh, I've seen which has come in C++23, and how this one would help us to express the intent and to address some of the use cases that we may have. Of course, this is an attribute, and you could have an assume attribute with an expression inside it uh, in your implementations, and the implementation at that point would assume that that expression is true. We have some situations where this assumption is built in. For example, if you have vector dot front, you know that it assumes that the vector is not empty. You might have a hash map or the length of a data structure where you want to assume that it is a power of 2 or something, because it would help you with the optimization. So this is a fine point, and I think I have a clip from the from Timur Dumler, who was talking about this feature. So it has its so you can say anything like this here. Assume that the point Timur was making was it is dangerous and it is a niche thing to be used for high performance implementations, but we'll see some examples today here. So this expression here may be potentially evaluated. It is not said that it will be called or evaluated, but this expression should may potentially be evaluated. If this results in a false, then it is undefined behavior. If this throws, then it is an undefined behavior. Uh, or if it is an undefined behavior, the expression is an undefined behavior, then the rest of the implementation here would also result in an undefined behavior. And how it helps is it helps the to tell to the compiler that you can assume certain things to be true and optimize based on that. Let's look at something here. With the vector example, I was with the two vector example. That's what we have been looking at in this talk. Uh, I was really tempted to say, assume that the two sizes are the same. Okay. And this is how you would actually state that the two sizes are the same. Okay. And beyond this, the compiler is now free to assume that they are the same size and might be able to um deal deal with the case uh, in an optimal way. But really, I don't think this is the right use of the assume variable. Assume is mostly for compiler optimizations and giving hints to the compiler. Okay. Here, uh, yeah, here we have Timur, who has who in his talk about C++ 23 changes has said this. I think I would play the clip here.
Attribute assume, this is something that's very close to my heart. I have spent 3 years standardizing this. It was hard, but we got it in C++23. So this is basically a feature where you can say assume expression, and then the compiler can assume that this expression is true without checking it, and then optimize based on that assumption. So that's very cool feature. If you write very low latency, high performance code, and you just squeeze the last nanoseconds of performance out of this particular piece of code where the compiler, the optimizer, doesn't quite understand what it is that you want. So this is now kind of a portable way to do this. It's cool, but it's also very, very dangerous, right? So you can easily just introduce undefined behavior into your program, and then everything goes off the rails and you get super weird stuff. So it's a very sharp knife that you need to be careful with. And there's also this feature still unreachable, which is kind of related.
Okay. So
So this is really cool, but
he's the
it's
author of this feature, and he was working to get this into the standards. And it is indeed a very fine point for high performance implementations. If the compiler is not able to you know guess some facts about your implementation. Okay, so here I've seen actually this kind of an implementation. We have a hash map implementation of our own in our implementations, and there we make sure that the size of the keys and the values is a power of 2. It really helps with the uh, with the implementation of that data structure, and it's a key fact about it. But when you iterate over that internal store array, the compiler doesn't know that it is going to always start at at an aligned offset for that data type. It doesn't know that it'll be always a power of 2, so it'll be divisible by the number of SIMD registers or the SIMD operations that you can do together at a time. So if you tell this fact to the compiler that the size of this array is a power of 2 or is divisible by 8 if you have 8 SIMD concurrently going on, then the compiler might not write the preamble and the postamble of that looping. It might directly jump into the SIMD vector instructions and might not have them. There is nothing to adjust because you are saying these things to the compiler. So that's great. Vectorization is the example. And I think this could even help with the kind of the restrict keyword that we have in C. But of course, undefined behavior is something that I would like to call your attention on here. And let's get so maybe in the zeal to optimize, uh, if you are ignoring some reality, you might run into a big problem with the undefined behavior. Okay, so danger there. Please beware. Okay, so just a look at the C language restrict. In C, if you have this function f, where the pointers p and q are being incremented, and you have a call to those here, it might be the restrict keyword there says that this pointer is uniquely pointing to something, and nothing else is also pointing to the same object. This for your compiler implementers or SOC implementers or uh, some people in this call would be very interesting. It's something that Darshan also had presented in his talk. Mahindra has mentioned about it. So if you have the restrict here, the compiler can assume that the P and Q are pointing to different uh, data items, and it it need not assume that something else would have changed. The previous line would have changed uh, the same variable, and it need not load it two times. It need not load it again from the memory in order to eliminate incorrect behavior. So because if p, as you see in the second call on the bottom, if both the pointers are pointing to a, it is the same variable, and you increment it by incremented by n. uh, Maybe the compiler didn't, if the compiler didn't think about the fact that both the pointers could point to the same data element and just added 51 time, it might happen. You will get an unexpected behavior, and that's a problem. So compilers pessimize this kind of an implementation if you don't have the restrict keyword, and they fetch again from memory. And correct me here, guys, if I'm if there's something to be added, or if you want to correct something.
I just want to add something, which is
Yeah.
very evident on the implementation of mem copy, right? So let's say you have now two things. You are copying from source to destination. So in hardware, right, different hardware, you can have instruction to copy a larger chunks instead of copying, like say byte by byte. And then if you have overlap, then there will
Mm.
probably start, right, because you are overwriting the data and then you are for a toss. So all the implementations of mem copy explicitly states that okay, this needs to be like two different memory segments, no overlap. So there is a restrict
No.
comes.
Right.
Yes. So if you pass both, then your for toss. Easy to understand thing. Yeah.
Right. So to prevent that pessimization, we have the restrict keyword in C language, but we don't have that in C++. I just pasted this example into Compiler Explorer with C++23 also, but it complained about restrict. So we don't have this facility, and the pessimization is guaranteed. We have no way to help. Well, now I think you can say assume that P is not equal to Q, and with the fact, uh, I think the assembly that is generated, uh, I was trying to look at this assembly with so much other code, and for lack of time, I could not pin down this one, that the generated assembly is optimal. But I think this would really result in the similar behavior as the restrict gives, and this would be beneficial.
Hi, Ankur. I was wondering about something.
Yeah.
Uh, in the CPP reference, we saw that the condition is potentially evaluated.
Yeah.
So I'm thinking, what if the assets in our code, if we replace them with assume? So,
No.
we, like, could that
Good,
be a viable idea?
good question, actually. I think they are both made for different purposes. The assert would not want you to proceed at all if this fact is not true, and assume would guarantee, would state that we expect this thing to be true, and the rest of the code would proceed with that assumption. So that's the difference. In assert, you would just not proceed to do other bad things if you faltered on the check itself. But here, the check may or may not be done, but this assumption would be made, like this is not truly going to check that P and Q are not the same, but it'll assume that, oh, it is potentially, it may check, but you're not guaranteed, right? So it's not that it is becomes conditional, or it crashes if it is not met. Oh, if it is
Uh,
not met, then it becomes undefined behavior. But because you can't guarantee, because the rest of the code which will be generated would be generated with that assumption, so it is undefined behavior, not that the compiler is going to start doing something else and different. Got it?
Ankur,
Yeah, yeah, makes sense.
Yeah.
yeah.
Thank you.
Ankur, I have a doubt with assume when with this we are saying that compiler will expect okay this will be true, but that's not a case always that it will be a truth. So isn't it, if I'll add this line in my code, I will make my code more vulnerable? Or
Yes.
who's the responsible? But now I'll have to make sure that this is this should be true always. So I'm adding that thing. Instead I would have used if else condition and I would have proceeded with the safety.
Yes. Very correct. This elevates the safety concerns. It is bringing in a problem which is not evident in the function and the API itself. But that's not the case every time. Here in your question, there might be a hint that the provider and the user are different and they don't know the internals and they don't know this fact uh, of assumption inside. But you might have some private implementations, for example, inside the vector. If you are moving things from, if you reallocated and you're moving the existing entries and adding the new entry which was inserted, then you absolutely know that the old and the new memory locations are by design they are non-overlapping. And so if you assume that these two ranges are not overlapping inside the vector, knowing the internal handling, you should be able to extract that optimal output from the compiler. So yes, in that so for an external API, yes, definitely it's a problem. But if you know what you're doing, like C++ helps you do this, if you are sure of the situation, you can go inside and do this. But if you are handing over that API to somebody else and they don't appreciate this part, and anyway, for an external API, it might not be a good assumption to make.
So, if from your answer, if I understood correctly, what I understood is means if I am sure that these will means if it is my internal implementation and I'm sure that these two will be a different memory locations, then I'll add this and compiler will optimize my code more efficiently. But if
That's
I'm not sure about that thing, it's not suggested to use assume here.
that's correct. This is why Timur Dumler also said that beware. This is a sharp edge.
Yeah. Okay. Thank you.
Okay.
I think it's better to say that if you know your data well, like what you are going to do processing, if you
Yeah.
know ins and out of it, so then I think that would make more sense to put this assume there, like whatever processing the data processing that you're handling. If you know so basically I think it's very well known data set, right? That would make more optimal use case there. But if you are dealing with something unexpected, I think then it's like basically shooting yourself in the foot. And
Exactly.
just yeah, I think
Okay.
that
Sorry, Ame, you were saying
no,
adding something.
I am done. Yeah.
Okay, thank you. Yeah, indeed, that's the point, and that's the risk. Okay, so don't do it at somebody else's home. Do it at your home. Okay, so not to confuse the assume with the likely and unlikely, that's a C++ 20 feature, which was introduced, and it lets you say that certain conditions are more likely than the others. I'm not going to go deeper into this, but I just got this screenshot from the CPP reference. Here, uh, the case one, as we see in this example, this attribute lets you tell to the compiler that one case is more likely than the other, or one case is less likely than the others. Okay, in case of conditionality, etc. So as we see in the example below on that screenshot, you have a switch on an int, and the case one is likely. Oh, sorry, case two is likely and case one is not likely. The compiler might be able to rearrange the instructions and get you more out of the processing here if you are able to say that. But again, this is also a sharp edge because these kind of likely and unlikely facts, they change over time in a code base, and you might not revisit a baked in assumption in a part of your code where you are saying that a condition is likely or unlikely. So it's also a risk that you're taking if you change this fact in the implementation as your product grows, etc. So beware. use this with caution also. But the assume and likely are doing very different things. And likely is just allowing you to optimize the branches, and the branch predictor may be able to do a good job uh, even without you specifying this. So take a call based on that. But we have this facility where you can say this to the compiler. And that is what I wanted to cover today, where you expressed your intent either to the compiler or out of the API and made sure that things won't go wrong.